Okay guys, let's take a look at this lesson. This lesson is where we are incorporating calculus or the parametric equations into calculus. We're going to look at the different ways that it is used. The first is kind of obvious with all of these problems up here, these equations. Here we see that we're dealing with our parametric equations. We have our derivative, first and second derivative formulas are different than normal derivative formulas because of the nature of the equations. We have two different equations. We have one that represents x, or the horizontal movement, and we have one that represents y, or the vertical movement. So therefore our equations are going to be a little different looking. We still, if we take a look at our derivative equation, we're still going to be looking for or needing dy dx. But we also know that on parametric equations, they have a t. That's why the derivative equation has to be a little bit different, because we still want dy dx, but our equations have t's in them. So this is the way that the derivative equation is set for parametrics. What we would do is we would find the derivative of the y equation with respect to t, and we would write it in the numerator. Then we would find our derivative of the x equation with respect to t. Notice it says dy dt, dx dt, and put it in the denominator. And that will generate for us this, the dy dx equation. So that's a little bit different. It's not the quotient rule, anything like that. It is taking the derivative of the one with the y and putting it in the numerator, taking the derivative of one with the x and put it in the denominator. Pretty straightforward, and we're going to practice this. The second derivative equation is just a little more troubling. It'll be a little more troubling to us because what we would think is, if we are following the pattern of the first one, we notice where we take the derivative with respect to t of the y one, put it in the numerator, take the derivative with respect to t of the x one, put it in the denominator, and we're good to go. On the second derivative one, it's just a little different. It's not quite that clean cut. And so it's something that you're going to have to rely on remembering the formula for. I mean, certainly there are proofs that set this up, but I don't really want to take the time to go over a proof that shows you where this was derived from. So we're going to have to just pretty much look at the formula and memorize it. So what we would do if we need the second derivative of a parametric equations, we would take our first derivative. Notice how we have our first, the dy dx, this one that we found previously, and we put it in the numerator and take the derivative with respect to t. That's what we do in the numerator. We take our derivative, our first derivative, put it in the numerator, do it with respect to t. The denominator is the part that's just a little troubling, because in the denominator the one that we had up here, the dx dt, we just put it here again, the dx dt. So that's what usually confuses students, because it's not intuitive, it's not what you would think. So we again take our first derivative, take the derivative with respect to t in the numerator, then we do our the dx dt from our first derivative, and that goes in the denominator. And again, we're gonna practice this. So probably the actual computations of the derivatives isn't difficult for parametrics. It's just remembering how to accomplish it, what to do. So let's look at our first example where they ask us to do that. They ask us to find dy dx and the first derivative and the second derivative. So let's do that. All right. So with the first derivative, and again, we're kind of focusing on our formulas since this is new to us. We're going to find dy dx, but notice how I have two equations. I don't have dx and y in the same equation. Certainly you could eliminate the parameter and take the derivative of it if you just wanted x's and y's, but that is not how this one, that's not how we're going to practice this one. You can't always easily eliminate the parameter t, so you have to know how to use these formulas and do that. Alright, so we're going to take the y one, with this one right here, and we're going to take the derivative of it. So dy dx equals, so the derivative of our y one, I'm doing this part. Dy dx equals, I'm just going straight into this formula. Okay? And we're going to take the derivative of the first one, which is 20t to the fourth minus 18t squared, and then the derivative of 3 is nothing. Notice again, the formula tells us to take the derivative of y with respect to t. That's what we just did. Now we're going to go to the denominator, and we're going to take the derivative of x with respect to t. So we're looking at this guy right here. And so we would get 2t. Let's see, the 9 is 0. Now, when you first start these, and again, this might be a pretty good idea when you first work them, is just do the dx dt separately. You know, don't jump straight to the formula. Let's just do them separately. If I do dx dt, I get 2t. If I do dy dt, I get the 20t to the fourth minus 18t squared, and then I put them together. So really, whatever you're comfortable with. If you want to do it in pieces like this, do the ones with respect to t and then jump to this formula, you can. If you want to jump straight to the formula, you certainly can do that too. It's whatever you feel comfortable with. So what we would do, since we're going to have to use this again, because they want us to find the second derivative, we should simplify it as much as we can. And this actually can be simplified quite easily into two different pieces. So this is going to be, what, 10t cubed minus 9t. So that's our dy dx. It is 10t cubed minus 9t. Okay. So now let's find our second derivative. And we're going to refer to our formula. So our second derivative, again, you can jump into this formula or you can do them separately. We're going to take our first derivative, which is this one, and we're going to take the derivative with respect to t and put it in the numerator. So we would have 30t squared minus 9. In the denominator, we're going to simply take the dx dt that we had found previously, which is right over here, and we're going to put that in the denominator. And that's our second derivative. So here's our first derivative, and here's our second. Now you can, if you want to put this into two different fractions, you can. This is going to stay a fraction or with a negative exponent, or you can just leave it like this. I mean, they're both as simple as possible. So that's just the mechanics of finding the first and second derivative. Okay. Let's take that a step further. Let's keep going. And what we're going to do is we're going to do some things that we're familiar with from our, Cartesian equations, the ones we've been dealing with, forever. We're going to find equations of tangent lines and things like that. So that's a normal thing for us to do, to write the equation of the tangent line. And if you recall, it's just, we'll just go y minus y1 equals m times x minus x1. That's what we're going to be filling in. We do need x's and y's, not t's. So that's the little bit of a, issue. It makes it different than the other ones that we've done. So we need the derivative. We need the dy dx. So we're going to use these formulas up here and find our derivative. I'm going to do them separately and then put them together. So let's do this one. So dx dt equals, so the derivative of sine is cosine, so 5 cosine t, and dy dt equals, see, the derivative of cosine is negative sine, so negative 3 sine t. And to get dy dx, which is the one that we need to find the slope, we just put, remember, the y one goes on top and the x one goes on the bottom. So the y one is on top, so our dy dx. And it kind of help you remember because, see, the dy is on top and the dx is on the bottom. So hopefully that'll help you remember where to place them. A common mistake that I see is students getting them mixed up. So we want to be sure that's kind of a clue. We want to put the y one on top and the x one on the bottom. So let's do that. The y one is negative 3 sine t over 5 cosine t. And our trig masters in here will immediately recognize that we could simplify it if we wanted to. We're going to be using it to do calculations with it, so it's your choice whether you want to simplify it or not. It's not our final answer, but I'm sure many of us can see that this can be written as negative 3/5 sine over cosine is tangent t. Okay, we're just going to use it for calculations. So, all right. So to find the slope, what we're going to do is we're going to take our t value that they give us. They want us to, that's where we're working with, and we would put it in here, and we would calculate our slope, our m. That's where we get our m from. So let's work on that. So the m, our slope, is going to be negative 3/5 tangent of 2 pi over 3. Okay, so let's remember our unit circle. 2 pi over 3 is 4 pi over 6, so it's this spot. Tangent is, as we said, sine over cosine. So what is that tangent value there going to be? It's sine, so it's root, yeah, root 3, and then so sine would be positive, and then cosine would be negative, right? Positive, negative. So it's going to turn out to be negative 3/5 times a negative root 3. Right, with me? And so we complete our arithmetic, and we get 3 root 3 over 5. Okay, so that's going to go right here in just a moment. So to find our x1, y1, when we have t's, we have x equations, y equations. So to get the actual x and y, what do you think we're going to have to do? We're going to have to sub it in, right? We're going to have to sub the t value into our x and y equations. All right, so x equals 5 sine, and our t value is 2 pi over 3. So x is going to be 5 times, again, we're at the same location. Our sine value up here, we agreed was root 3 over 2. That's positive because it's sine. This is y. So root 3 over 2. So our x is 5 root 3 over 2. Now let's work on the y. Y is 3 cosine, and our t value again is 2 pi over 3. Okay, so cosine over here is negative, right? And its value is 1/2, right? Negative 1/2. So we have y equals 3 times negative 1/2, and that gives us negative 3/2. Now we can write our equation, and we are done. So y plus 3/2 equals, our slope was 3 root 3 over 5, and then x minus 5 root 3 over 2. Kind of messy, but pretty straightforward, just the way we've been doing those before, just with a different kind of equation. Okay? All right, let's move to the second page. I have a couple of problems over here that we're going to look at. Okay. The first one is find all points of horizontal and vertical tangency given the parametric equations. Okay, let's think about this for a second. Horizontal tangents occur when the slope of dy dx is what? Is 0, right? Vertical tangents occur when it's undefined. So that's really what our task is. Our task is to find dy dx and set the top equal to 0 to find where our horizontals are, the bottom equal to 0 to find where our verticals are. Right, you with me? That's all we're doing here. It sounds kind of really complicated, but it's pretty basic stuff we've been doing before. So let's find our first derivative. Okay, so you can do it in pieces, or you can jump straight to the first derivative, whatever you want to do. Okay, so let's just do it in pieces. dx dt is going to be 6t minus 6, and dy dt is going to be 2t minus 8. So therefore, dy dx is going to be, we put the y one on top, 2t minus 8 over 6t minus 6. If you wanted to make it easier to calculate with, you could take a 2 out of the numerator and denominator. It's just 1, right? And get rid of the 1 if you wanted to. That would be fine. So we factor out a 2 from the numerator, a 2 from the denominator. We get t minus 4 over, 3t minus 3. And so that's our derivative. Okay, so if we want our horizontal, so let's work on the horizontal tangents. We agreed that that's where the derivative would be 0. In other words, where the numerator would be 0. So that's going to happen at t equals 4. I set the numerator equal to 0. I get t equals 4. And it wants the points where that's going to happen. So basically, to get the points, I just get them out of here. I just go back and I plug the 4 in for x and y, and I get my point. And that's all there is to it. So to get the x coordinate, I'm going to plug the 4 into that. So 3 times 4 squared minus 6 times 4. So help me with my arithmetic. I got that to be 24. Hopefully that's arithmetic good. 24. Okay. Then my y is going to be 4 squared minus 8 times 4 plus 9. And I got that to be a negative 7. So my point for the horizontal tangency is 24, negative 7. Okay, so that's for my horizontal. Okay, let's work on vertical. My vertical is where the denominator of my derivative, my first derivative, would be 0, which is at a t of 1. Okay, so then I substitute that in again, same way we did before. X equals 3 times 1 squared minus 6 times 1, and that gives me a negative 3. And my y equals 1 squared minus 8 times 1 plus 9, and that was a 2. Arithmetic okay? Okay, so then my point of tangency is negative 3, 2. There's for the vertical. Okay. The last thing that we're going to look at is our basically curve, to find the arc length, the length of the curve. We know of an arc length formula before that we used. Remember when we were using it on Cartesian equations? And this is actually it right here. Hopefully we remember that. All of this is just finding the formula for parametrics. That's all it is. You don't have to memorize all this. It's for those of us that are curious and want to know where it came from. You can peruse that. If you're really not curious and not really concerned where it came from, we can go straight to basically the formula. The formula in the two notations that we use. If we use dx dt and dy dt, we can look at this formula. Notice the difference. Let's compare and contrast this parametric arc length formula with our original arc length formula. And they are pretty close. They look very close, right, to each other. Our original formula was a 1 plus the derivative squared. And our, again, this takes you through the whole process of how we get to this formula. But our parametrics curve length formula is very similar, but we do dx dt squared plus dy dt squared. That's the formula. And this is just using function notation. It's the same formula. Now, a note that we need to make is that, it's down here on the bottom, that this formula works when the curve does not intersect itself on the particular interval, so it can't cross over itself. So that's when this works. And it must be smooth. We can't have like, it's got to be differentiable. It's got to be smooth. No jagged edges like a corner or a cusp or anything. Okay. And on this last example, we're just going to set up the integral. We're not actually going to calculate it. On one like this that we're working with, we would use a calculator. You know, this might be a multiple choice question on the calculator portion of the AP exam, where we would set it up and use a calculator to get the value, because this one's pretty complex. We're just going to set up the integral. Okay, so we would need to, our bounds is the first thing to look at, and so our bounds are from 0 to 4. We have our square root guy right here. Then I need to find the derivative of, I need to do dx dt and dy dt. So let's work on this one first, dx dt. The derivative of e to the box, or e to something, is e to the box times the derivative of the box, from back in the day when all we had to worry about was derivatives. So that would be, let's see, derivative of 5t plus 2 is 5. So we'd have 5e to the 5t plus 2. And we're going to show that squared. I don't recommend simplifying it. I mean, you can if you want to. I would put it in my calculator just like that. I wouldn't simplify it first, just for fear I might simplify it incorrectly. And then we're going to do the dy dt. We're going to take this one. So it's another chain. So the derivative of sine is cosine, but we have to chain it. Remember that? So it's going to be, what, 2t, actually 3 times 2, so it would be 6. 6t sine, oops, derivative of sine is cosine. Okay. Cosine t squared, all of that squared, dt. So we're just setting up the integral. We're not going to evaluate it or stick it in our calculator. Okay, is everybody okay with that? Okay.